Today we are we are starting our third module, which is mainly dealing with the random process. So welcome to this session. So moving to our objective, today we will introduce what is a random process and what is the definition of a random process, and we have some terms like ensemble, stationary, all those things, and the probability density function of a random process. Also we will discuss about the expectation of a random process. So moving to the introduction, we'll discuss an experiment. See, consider an experiment of throwing a die in every minute and observing the data. So normally what we have done in the previous classes or previous examples, what we have seen, we did the experiment and we don't bother about the time where we did the experiment. So we just do the experiment and see what is the outcome. For a die, if you throw a die, you have 6 outcomes, either it may be 1 or 2 or 3 or 4, like that. So now if I am going to do this experiment in every minute and I am observing the data, then I can draw the graph like this one, which consists of the time axis is there in the x-axis and y-axis the outcomes. For example, at time t equal to 1, you got 4 as the outcome. At time 2 equal to, you got 1 outcome, and the die gave number 6 in the third minute. In the fourth minute I drew the die and I got the value 4. In the fifth I got 2. For example, this is a random process. I cannot determine what value I will get right when I throw the die. So this is one of the example. Now what is x actually? X is actually the random variable. So what is the random variable? It is the outcome of a die, throwing a die. So what are the elements that comes in set x? X consists of 1, 2, 3, 4, 5, 6. So these are the elements in x. Now, does this x is a random variable? Yes, it is a random variable. But does x always give the same outcome? Now we will see another experiment, the same one did by another person in the same time t equal to 1, 2, 3, like that. Now if it is the experiment, he may get another graph. In the first time he got 2, then he got 4, then he got 2 again, then he got 1, then 6, then 1, like this. So generally what we can say that x is a random variable, but x depends on two things. X may give an output as x, but also it is a function of time also. The first time t equal to 1, I got a value, and that value is small x, and it is t1. So I can call this as x1. This is t1. This is x2 at a time t equal to t2, and this is x3 at a time t equal to t3. Now if you say the probability here, what is the probability of getting 4 when time t equal to 1? Then I can say probability of x being equal to 4 when t equal to 1. So this probability function depends on 4 is a small x, and 1 is a small t. So this is a function of x comma t. So such random variables which are dependent on x as well as t are called a random process. Now I will give another example. For example, this one, you see this one. For example, if the axis is time and this is a voltage generated by a sensor, the voltage generated by the sensor may be like this one, right? It may like in millivolts, maybe a noise generated by the sensor. So what is this noise actually? Noise is random. We cannot predict at what time what value we are getting, but we can say at time t equal to t1, what is the probability of getting voltage is equal to v1. So the variable voltage has two values which depends on v1 as well as t1, and we can predict the probability that the v can become v1 at a time t1. For that there is a probability. So such things which depends both value as well as time are called a random process. Now what is the difference between this one as well as this one? What is the difference? The difference is this one is a discrete time. It is not continuous. Instead it has values only at t equal to 1, t equal to 2 like this one, and but this has values in for all the possible values of t starting from 0 to infinity. So that is what a random process. Now you can see another example which fairly given here. So what is this? This will be a discrete time. This is actually daily average temperature. So the day 1, day 0, what is the temperature? Day 1, what is the temperature? Average temperature. Day 3, what is the temperature? Day 4, what is the temperature? Like that. Now this is a stock price. Stock price, we are getting the stock price at each and every hour or minute of the day. So that stock price changes continuously with respect to time. But here it is like average value. So day 0 it has value and day 1 it has value. There is nothing between 0 and 1. So these are discrete, these are continuous. So this is discrete, this is continuous. Moving to the next topic, that is, so we have discussed about discrete time random process as well as continuous time random process. So generalizing, we can define as a random process is a family of random variables which consist of x of t, where t belongs to t defined on a given probability space indexed by the parameter t. So x was there initially when we studied random variable. Now that random variable depends on t also. So where t varies over index set to t. Now if this index set is a discrete set like 1, 2, 3, 4 etc., then it becomes a discrete parameter, and if this is a continuous starting from 0 to infinity, then it will be a continuous random process. So the index set t is called a parameter set. Remember, this is the definition, and the values assumed by x of t are called states. Now what is this experiment? Every time we have throw the die, so what is the value it can take? Like a t parameter set can take the value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity, whereas the parameters, the state space is like state values can take the values 1, 2, 3, 4, 5 and 6 on. So that is the difference between parameter set and parameter state, the state values. So another important term in this experiment is the ensemble. Now what is an ensemble? Ensemble is the collection of all possible sample function is called ensemble. So we know that for example we observe the voltage x1 of t, noise as x1 of t as a function of t, and the noise is a random variable. Noise is a random variable which changes randomly with respect to time. So it can take the value, for example, 0 to -1 to 1. Now this is a random variable. Now if somebody else observes the same experiment, he may get another different set of values. The values which I have here is not same here, but it started at 0, this started at 0, but this has different value. Now if another one does the experiment, see, this is this value, this value, this value, these all are different at a particular t. So this entire set is a random process, this is another random process, this one is another random process, but all belongs to the same process. Their outcomes are x1 of t, x2. So how many outcomes we may have? We don't know the value correctly, right? So we don't have a unique outcome always. So it may be x1 of t, x2 of t, x3 of t, etc. We may get x infinity of t, because we have infinite possibilities of getting a noise voltage. So all these values are called possible values of graph functions are called ensemble. Just like we have the sample space in random variable, here it is ensemble. Now the probability distribution. So now the probability distribution function was generally represented as fx of x, right? So what was fx of x? Fx of x was probability of x equal to x, because in random variable it is only x, it depends, but in the case of random process it depends on time also. So fx of x comma t is represented as probability of x of t, the function of that variable becoming x. Okay. So for example, f x of 2 comma 3 means what here? So this is x, this is t. So fx of 2 comma 3 for a throwing die experiment. So getting a 2 at the third minute, or when throwing the third time, what is the probability of getting a 2 while throwing it third time? Okay, third minute. That is called the probability distribution for a random process. So that is represented as a function of both x as well as t. So that is probability distribution density function. If it is a discrete, it will be mass function, and probability distribution function or cumulative distribution function CDF is represented as capital Fx of x comma t, which is nothing but probability of getting x of t1 lesser than or equal to x1. So similarly we can say that Fx of 4 comma 5 is what? So it is nothing but probability of x of 5 lesser than or equal to 4. That is nothing but probability of getting of at least what is it called, the maximum 4, 1, 2 or 3 or 4 in the fifth minutes throw of die. So at this time, what is the probability of getting either 1 or 2 or 3 or 4? So that is called the dense cumulative distribution function. Now if it is a second order, there will be two variables like x1, x2, t1, t2. So it is like joint bivariate distribution only. Probability of x equal to t1 comma x of t2 equal to x2. So this comma here means and or intersection. So nothing but x of t1 equal to x1 as well as x of t equal to x2, both should happen. If both are happening, then it is called a second order distribution. So similarly we can explain capital Fx of x, x1 comma x2, t1 comma t2 also. Now nth order distribution, just extend this one up to n and t also to n. So it is nothing, probability of x t1 is equal to t1, x of t2 equal to x2, etc. x of tn equal to xn, and capital is like x1 less than x1, x of t2 less than x2, etc. x of tn less than xn. So expectation of this one. Now for example, for the univariate case or the first order distribution, the mean is given by expectation of x of t. So we know the E operator is nothing but it is minus infinity to infinity is a term which comes in this one into f dx. So here f is nothing but fx of, since it's a random process, it is a function of both x and t, but we want x, so the variable is random variable is small x. Here both x and t is not required, only x is required, remember. So the differential term element will be dx only. So similarly we can describe variance also. Sigma x square of t is equal to variance of x of t minus infinity to infinity x minus this mean into fx of x comma t dx. Moving to a bivariate case, you have two variables x of t1 as well as x of t2, x1 into x2 into fx of x1 x2 t1 t2 dx1 dx2. So it is same as bivariate case what we have discussed, but only additional thing is there is a time parameter. Now we will move to an important term called stationarity, a stationary process. Now we will see some examples. This is the amount of flow of water in Nile, river Nile, in different cases. This is available in the R software. So the amount of water flow in different years in 1880, so every 20 years it is measured, so each time it is, so this is a continuous random process. So why it is continuous? It has a value in all the possible points starting from this to this, minus infinity to plus infinity. So what about this? This has some statistical parameters, like it has a mean, it has the variance. What is mean? Mean means the average of this one. This may come like this, right? Now what is the variance? Variance is the maximum difference. This is variance actually. So if you see this graph, what is the thing what we can observe is that the mean remains almost the same, right? Whereas this one also. So we can say if mean and variance remains almost the same, the probability distribution function remains almost same from the beginning to the end. Now see another example where we have the temperature measured for different time intervals, different months of time. So average temperature per day it is measured and it is plotted from 1920 to 1940. So this is also available in our software. So if you see here, the value is like a harmonic, it repeats whatever done. So this is one set, the same set repeats again here, same almost repeats the same here. So like this it is going on repeating. So here mean and variances are different, but this is a repeating or harmonic. Now what about this one? This is the number of air passengers of some particular air company starting from 1940 to 1970 it is plotted. So what is here? Now if you take the mean of this one, what happened to the mean? Mean goes on, mean means the average value of these sets. The mean goes on increasing. Even the variance means the set of range of values. If you see here, it is more, it is more, it is more like this one. If mean and variance changes, fx also changes, or fx also increases as is. So it doesn't have a same distribution as it has in the beginning, but the distribution goes on changing. Now understanding these graphs, we can define a stationary process. So among these three graphs, which is more likely to be stationary, if you see these three graphs, this one is for the flow, this is for the temperature, and this is for the air passengers. If you can see, the mean almost remained and variance almost remained in the first. So this process is almost stationary. We can say this process is almost stationary. This is not completely stationary, but almost stationary. Now understanding this concept, we can define a random process is said to be stationary, or it is almost called strict sense stationary. Strict sense stationary SSS process if for all n and for every set of time instance t, the x1, x2, xn, t1, t2, tn is same as that of after a particular interval of tau. It should repeat the same. Now what is the value of tau? Tau may be, the tau is not a constant, it should be for any tau. So this function is said to be strict sense stationary whenever whatever value of tau, whatever value of n, for example only 3 are taken, tau is taken 0.1, so after 0.1 it should repeat. If tau is taken 0.2, after 0.2 the function, the probability distribution or the density function should repeat. This is for distribution, this is for density. Now after this tau, the value should repeat. So can we say that in the first graph it is repeating? No, but it is almost similar to, this is the ideal situation. We cannot idealize, but we can approximate this graph almost strict sense stationary, means its probability distribution is repeating or remains constant, almost constant. So such things are called strict sense stationary processes. Now, what is non-stationary process? Then whichever not stationary, they are non-stationary process. Now we'll consider a first order stationary process. Now first order stationary means order is 1, that is in this term the n value is 1, tau can take any value. So if you substitute that one, fx of x comma t, fx of x comma t plus tau, right? We don't want x2 to xn and t2 to tn, so here also only one variable. So instead of t1 I am taking t, and here it becomes t plus tau. So fx of x1 comma t is fx of x1 comma t plus tau. So that is what we have here. So for any tau, so this means that fx of xt is for any tau. If tau equal to 0, this is fx of x comma t is fx. If 0.1, 0.2, any value, the value remains same, means I can, this is not depending on t. Can we say like that? If for any tau the value remains same, means if the graph, if I plot, this is the value of f. So here it is, for example, 0.5. Now t plus tau means somewhere here. So I took tau as this much. So there also it is 0.5 only. It should not be same. If I took tau is 0.25, then here also it should be same. If I took 0.1, then here also it should be same. Means the value of fx is not at all changing. It is remaining constant throughout. So I can write it as fx of x. So fx of x comma t, no need of t, so it does not depend on the variable t, it is independent of t. So fx of xt can be written as fx of x. Now capital Fx of x comma t is fx of, sorry, it should be capital Fx of x. So the mean will be, so it does not depend on t, so you can write mu x. Here also it will not depend on t, so you can write sigma x square. So this is the expression. So this is the first order stationary process. Now what is second order? The number of terms becomes 2, here 2. So x1 x2 t1 plus ts, t2 plus ts. Now this is for any value of ts, it should repeat. So two pairs together we have to repeat that. For example, if this is x1 of t1 has the value this much, and this is x2 of t2 has the value this one. If I shift this one by a value ts, the graph should repeat. Both t1 should repeat as well as at t2 what happened, that should repeat. So this case, if it happens, then it is called, and this is f here, this is time here. So this cases, then it is called second order stationary process. Now we know that t1 plus ts, we can take it as a t. Then t2 plus ts is t2 plus, here t minus t1 is ts. So I can substitute t minus t1, or t plus, I can bring this one here and t2 here. So t plus t2 minus t1, or instead of t2 minus t1 I am using a constant term called tau. So t plus tau. This means that fx of x1 comma x2 comma x1 comma x2 comma, instead of t1 we have t1, t2 we have t. T1 plus ts is called t, and t2 plus ts is t plus tau. Now for any tau. So what is the significance of this expression? So which means that the expectation of x of t1 comma x of t2 will be x of t comma x of t plus tau. So irrespective of value of t, it depends only on tau. Means you have to take a x of t, this is x of t, and you have to take x of t plus tau, means it is shifted version of the same, and you have to multiply each and take the average. That is called autocorrelation, that you will study in the next. But when you take this case particularly, this is a second order random process, and it is called a weak sense stationary or wide sense stationary process, or generally we call it as WSS. Now weak sense stationary is a strict sense stationary, but all stricter we cannot say as a weak sense stationary, because what is the definition of strict sense stationary? Strict sense stationary should happen for all values of n, for any value of tau also. Now wide sense stationary is only available for n is equal to 2. So this is about the basic concepts of our topic. So I'll stop here. We will discuss about this one further in our next class. Thank you.